All right, so now that we've talked about Faraday's law and Lenz's law, we can look at a particular instance where we get an induced current, and that's when our conductors are moving through magnetic fields. And so this is termed a motional EMF. Turns out that you can explain the motional EMF just by using the force law for charges moving through a magnetic field. But we're going to start with leveraging Faraday's law, and then we'll explain how you could get the same result using force analysis. So I've got a loop here moving to the left through a uniform magnetic field, and so the loop is entering the magnetic field. And so what that means is that the magnetic flux through the loop is going to be changing as the loop enters. And so if we want to talk about the flux in the loop, we have to look at the integral b dot dA. And so the dimensions are listed over here. I've got so x is essentially the amount of the loop that's in the magnetic field. L is the sort of height of the loop, and the speed v is essentially the rate at which it's moving into the magnetic field. So for the flux b dot dA, the magnetic flux is BLX, right? So that's just uniform B field multiplied by the area of the loop. And then if you take the derivative with respect to time of that, you end up getting BLV, because B is constant, L is constant, and dx dt is the speed. And so the induced EMF, as this loop moves into the magnetic field, is VLB, right? Where again, that negative sign corresponds to the direction. So if you remember with Lenz's law, we can also come up with the direction. If you see what's happening in this loop, the magnetic flux through this loop is going to increase as the loop moves into the magnetic field. So that means as it moves in, more and more of the field pointing into the page, right, cuts through the loop. And so that means we need an induced current that opposes that increase in the magnetic flux. That means we need a magnetic field that's pointing out of the page. And so we're going to need a current induced in that direction so that the induced magnetic field inside the loop is coming out of the page. All right, so that's using Lenz's law to get the direction. Now, the induced current is just simply Ohm's law. And so if the induced EMF is VLB, then the induced current is VLB over R. Now, one thing that we didn't mention up here is that it turns out for the loop to enter into this magnetic field and continue at a constant speed, there actually needs to be a force pulling it or pushing it along to maintain that speed. Essentially, the magnetic force on the portion of the wire that's moving through the field would essentially cause the loop to slow down. So to keep moving at that speed, there actually needs to be a force applied. And that's the focus of what I have down here at the bottom. So as the rod, so this is essentially the same idea, but now it's the rod that's moving as opposed to the full loop. And so this picture here is essentially the same as above. It just is a little easier to talk about the applied force in this case because it's the rod that's free to move on the stationary rails. And so here we've got a rod of length L, and the induced current that's moving through the rod, well, that rod is in a B field, and so there's a magnetic force to the left on that rod. And so if the rod is going to continue to move at a constant speed, there needs to be some applied force, some pulling force, right, that maintains that speed as constant. So essentially the magnetic force and that applied force have to be the same value, right? So this part right here. So again, that applied force is what's needed to keep V constant, and that is sort of hidden up here, right? It's not actually clear that there needs to be a force applied to keep this V at a constant value, but it turns out that that is the case. And so we can talk about the power that's supplied to this circuit, to this loop, as it's moving through the B field or as this rod is moving. And that power supplied comes from the force that's being applied. And so that's this expression right here, the force applied multiplied by the speed at which the rod is moving. And again, that applied force has to be equal to the magnetic force. Well, the magnetic force is ILB, and I, induced, is VLB over R. And so if you plug all of those things together, you end up getting that the power supplied to the circuit is V squared L squared B squared over R. Now, since we have conservation of energy, when we determine the power dissipated by the circuit, we should find that it's the exact same amount of energy as what's supplied. And so if you use the expression for the power dissipated by a resistor in a circuit, then you find that, yes, actually the power dissipated is in fact the exact same amount of power that was supplied or generated. And so the motional EMF, right, this battery that's produced because the conductor is moving through a magnetic field, that motional EMF is essentially set up by the applied force that's causing the conductor to move through the field at a constant speed. That EMF introduces an induced current in the circuit, and so there's power supplied by the applied or the external force, and the circuit dissipates all of that power. And so rather than an EMF being generated by, say, chemical means from a battery, here it's the motion of the conductor through a magnetic field that generates that EMF. So an interesting question is why is it that these changes in magnetic flux, why is it that there's induced EMFs, induced currents generated? And the amazing thing here is that what we're discussing is that there's this fundamental connection between electricity and magnetism. And it turns out that when you change the magnetic field, right, if the magnetic field is changing with time, that actually produces electric fields. And so this is going to be fundamental to what we do in the coming weeks as we move into talking about electromagnetic waves. And so it turns out that changing B fields induce or create electric fields. And it turns out that changing electric fields induce or create B fields. So this picture here is one of the previous examples where we had let's see if I can get this. We have a loop of wire placed in a magnetic field, and that magnetic field is decreasing with time. And so if we think about Lenz's law, we can immediately figure out that there has to be an induced current in the wire because the magnetic flux through the loop, so remember, the magnetic flux corresponds to the B field through the area of the loop. Well, that flux has to be changing because the B field is decreasing in strength. So the flux is changing, that means there's an induced current, and the induced current in the loop has to be in the direction so that the B field that's produced opposes that change in flux inside the loop. So we've got a B field, external B field coming out of the page, but it's getting weaker. So we need an induced B field inside the loop coming out of the page to oppose that decrease in flux. And the only way we get a B field out of the page inside the loop is if the induced current is counterclockwise. All right, so that's Lenz's law. We know there's an induced current. The question is, why is there an induced current in the loop? And the really cool thing here is that when the magnetic flux in a region changes, that change in magnetic flux produces an electric field, and it produces an electric field that is fundamentally different than the electric field that you get in electrostatics. In electrostatics, if you went around a closed path, E dot dl had to be equal to 0 in electrostatics. And in electrodynamics, or in what we're talking about right now, it is no longer the case that if you go around a closed loop, that the electric field dotted into the path, it is no longer the case that that will add up to 0. And so what I've drawn in this picture are all of these red circles. These are just random locations that I selected in the region where the B field is changing. And so these are electric field lines that are being produced by the changing B field in this region. And so if you happen to have a wire located in the region, like right here, well, then you're going to have a current in that wire because there is an electric field that has been set up. The electric field is there whether there's a wire or not. And so the field lines that I've drawn here, those are distortions in space due to the fact that the B field is changing in that region. And if you happen to have a conductor in that location, then you will get a current, right? So it's really an incredible thing. Now, that brings up the idea of an eddy current. So since E dot dl, that path integral, doesn't have to be 0, if you have a conductor, then if the B field is changing in the region where there's a conductor, you will get loops of current. And so that's what I've got in this picture right here. I've got a B field pointing up through a conductor, but the B field is decreasing. That is going to induce a current in the conductor. And these are called eddy currents. And one of the really interesting things here is that means that materials that aren't normally magnetic, say copper, if they are present in a region of space where the magnetic field is changing with time, magnetic moments will be induced in the material, and essentially it will act or behave as though it were magnetic. So this is a very useful and interesting phenomena. Some of the interesting applications, the book talks about magnetic braking, and so you can induce these eddy currents, and then you can have your conductor interacting with the magnetic field such that it slows down, so you can cause things to slow down or even stop using magnetic braking. You can also induce currents in the conductor and have the material heat up, and this is essentially what happens with induction stovetops, where you can place your say hand on top of the stove and not feel any heating sensation, but put something like a copper pot on top of the induction stovetop, and the material heats up incredibly quickly, again due to these induced eddy currents that are essentially energy through heat throughout the material, and allowing you to cook food or heat up water very efficiently and safely, again, because if your material is not a good conductor, then you will get very small or negligible eddy currents, and you won't have the same phenomena.